And I'll ask Anastasia to share her transparencies. So we're switching again now in a more mathematical direction to Anastasia Volovich from Brown University, who will tell us about the symbol alphabet from Plabic graphs and tensor diagrams. Plabic, if I'm not mistaken, is an abbreviation for planar bicolored, but you'll correct me if I'm mistaken. Please.
All right. Okay, so hi, everybody. It's great to be here. Thank you so much to the organizers for inviting me to speak and for organizing this great conference. Although I have to say, I always love to visit Copenhagen, and I really, really wish it happened in person. But hopefully, okay, next time. Okay, so my talk is going to be about n equals 4 Yang-Mills theory. And I'm going to tell you how to get the symbol alphabet from two things, from Flabby graphs and from tensor diagrams. This is going to be based on a series of papers that are listed here that I wrote in the last year. So this is work with Mark Spradlin, who's hopefully here, our current postdoc, who hopefully is also here, Akshay Yalishpur Srikant, former student of NEMA. So now we're very lucky to have him at Brown. My former student, Anders Schreiber, who is now at Oxford and moving on, I think, from Oxford to Munich, I think in the fall, in October. And my current two students, I hope they're also here. So it's Jorge Margo, who is starting his 5th year and will be graduating next year. And Li Chen Reng, who just finished his 2nd year. So he's moving on to his 3rd year of his PhD studies. Okay, great. And hopefully they're all here and they can also participate if needed. So you can see the pictures right here. Okay, very good. So let me start with the introduction. I'll be talking about planar n equals 4. And as you heard from other talks, the amplitudes in this theory have been computed to very high loop order. They've also have many remarkable properties that have sparked interest from mathematicians who work on combinatorics, algebraic geometry, and number theory. At the same time, the methods that we've been developing over the years for this n equals 4 are directly applicable, and some of them have been applied to actual QCD computation. So it's on one hand, it's a great mathematics. On the other hand, the methods that we used are actually useful, although we are studying n equals 4 Yang-Mills theory. So what I'm going to do, I will start slow. I will review some recent developments in the computation of amplitudes in this theory, and then describe some approaches that hope to explain some of the properties of these amplitudes using various mathematical constructions. Okay, so here's the outline of my talk. So you had an introductory slide right there. So I'm going to then talk about very briefly, it's going to be a review of status of the computations, just one slide, and then some of the tools that are widely used. Some of you have heard this before, but to my surprise, I noticed looking at the participants list that there are a lot of people who are new to this. You might have not heard this. So this is the time for you to listen, but there are a lot of plenty of experts in the audience who've done those computations. So please, you can, go do something else, have your coffee during that time. So then I'm going to move on to, so I'm going to slowly increase the number of points. I'm going to describe for you, review for you, remind you that for 6 and 7 points amplitudes, they're very nicely described by cluster algebras. And the main focus of my talk is going to be 8 and 9 point amplitudes. So for 8 and 9 points, there'll be basically 2 new features that emerge. Number one, you're going to start seeing square roots of some local coordinates. And number 2, the cluster algebra becomes infinite dimensional. So you have to start developing new methods. So, and I will present to you 2 of our approaches to trying to explain some of the features that we see for these amplitudes. So number 1, would be from Plabic graphs, and number 2 would be from tensor diagrams. So these are kind of two complementary approaches. I'll comment on both of them and try to describe what we understand and what we know. Okay, great. So can you see my pointer when I point? Actually, David, can you see the pointer? Like,
yes, we can.
Okay, perfect. Okay, so the status. Okay, so
although if you can make it a circle, it might be more visible.
I don't know how to do. Actually, I don't know how to do it. So let me just not. I have limited time. Okay, so what is the status? Okay, very good. So due to the seminal work by Baer, Dixon, and Smirnov, 4 and 5 point amplitudes are known to all loop orders via the BDS ansatz. Now, also because of the dual conformal symmetry. So 4 and 5 are known to all loops. We're going to start, as I said, we're going to start increasing the number of points. So the 6 points are known through 7 loops, and 7 points are known through 4 loops. So this is due to the work of a lot of people, Dixon and collaborators most notably. So there are a series of a lot of papers, and I'm not listing them all. So instead, I'm encouraging you to open this review by these authors, who many of them are also in the audience. So please forgive me for not listing all your 20 papers. So these are remarkable computations, and I refer you to this review. Now, as we start increasing the number of points, I actually learned on Monday. Unfortunately, I didn't go to poster session. And so luckily, the organizers posted the PDF, and I went to the PDF of the poster session. I noticed that there's a slide number 33, that it turns out that that Li and Zhang have the computations which they claim to IP. I haven't talked to them. I just looked at the slide that MHV 8 points, they computed through 3 loops, which is quite remarkable. So this I learned on Monday only. So I added quickly this to the talk. Then when we start increasing from 8 to 9, so MHV and NMHV have been computed in the last year by, again, Songhee, Li, and Zhang, so 2019, 2020, and that's basically where the focus of my talk is going to be. Okay, so I won't have much to say about these extra, I will mention them, but I won't have much to say about this, but my focus is going to be here. Now, of course, if we just want MHV, just the MHV have been known through 2 loops due to the work by Simon for over a decade. Okay, so that's where we stand. Hopefully I didn't omit anybody, but that's the situation. Okay, so very good. So the methods, how are these computed? Again, I stole from this great review. So they're not computed, of course, by doing any Feynman diagrams. They're computed by Amplitudes bootstrap. So what these authors do, they write down an answer as a linear combination of functions and determine the coefficients by solving a system of linear constraints. Okay, so it's easy to say, but it's a very, very difficult and important computations. So here, for example, I stole this table from this review. So they start, for example, if you are at, this is for 6-point MHV and NMHV amplitudes. So for example, for 6 points, you start with something which has this number of parameters, and then you start applying various constraints, such as symmetry, collinear limit, multi-radial kinematics, etc., until you finally get a unique solution. So this is really remarkable. This is a very high constraint system with lots of parameter. So to me, it's remarkable that there's a unique solution that exists. Okay, great. So that's this is how all this. So again, most of these experts are in the audience, but for the rest of you, this is approximately how these high loop computations are done. Okay, so some of the tools that will be important for my talk. So we're going to be talking about these amplitudes. They're going to have 2 parts. They're going to be some functions. They are functions of some variables. So functions and variables. So who are going to be the variables? Well, normally they're, the amplitudes are functions of momentum. Here, everywhere, instead of momentum, I'm going to be using momentum twisters. So we will be we go usually to P3 and label amplitudes by n points zi. I labels the particle number, so it runs from 1 to n, and they live all in P3. And these are called momentum twisters. The dual conformal symmetry is SL4C. So then there's a natural SL4C invariant denoted as IJKL, which is nothing but the determinant of ZI, ZJ, KZL. So everywhere you're going to see these brackets. So amplitudes are function of these brackets. Okay, so everywhere you will be seeing these brackets IJ, KL. Very good. So number 2, the functions. So we have the following dogmas. So what kind of functions are we looking at? The MHV and NMHV L loop amplitudes can be expressed in terms of multipolylogs of the weight, which is twice the loop number. Of course, at higher points, for example, at 10 points n cubed MHV, you have elliptics. There'll be several talks at this conference on that. For the purpose of the case of the amplitudes that I'm looking at, we'll be restricting our attention to only multipolylogs. So who are these multipolylogs? These multipolylogs can be defined recursively. You take the weight m multipolylog, you take the differential, and you write it as a multipolylog m minus 1 g log, and you continue. Finally, what you do, you take the arguments of all these logs and take a tensor product of them, and that's called, as many of you know, is a symbol. So for example, for Li2, you take the derivative of Li2 and you write it log 1 minus z g log z. So the symbol of Li2 is minus 1 minus z tensor z. So the collection of all these arguments that appear in the logs is called symbol alphabet. So that's one of the words in my title. So you have these amplitudes, these polylog functions, and the arguments of cleverly organized arguments of these functions. That's the symbol alphabet, and it appeared in some other talks already. So the physical meaning of that is that it encodes singularities, and it also serves in input in the bootstrap. So the subject of this talk is the symbol alphabet. So what do we know about it? So what do we know about symbol alphabet for n equals for Young-Mills theory? So let's just start increasing the n. I remind you. So for 6 points, this symbol, so this amplitude has been known for over 12 years, starting with the work of Del Duca, Duran, Smirnov. And so we know that the symbol alphabet is given by these 15 letters, which are nothing but the GR46 Pluka coordinates, A plus 1 BC. And if you want an amplitudes, there, as I said, this is a polylog function. So roughly speaking, it will be Li4, and then you have all these functions. So now for the experts, of course, I am going to call it 15 letters, but of course we know because of dual conformal invariance, the amplitudes organize themselves as a function of these dual conformal cross ratios. So you're more familiar with 9. So I'm going to just for comparison with mathematics, I won't talk about 9. I'll have 15 minus 6. For 7, of course, it's also been known for over a decade. The symbol alphabet is given by 49 letters. So you have the GR47 Pluka coordinates, you have 35 of them. And then you have, in addition, you have 7 plus 7 cyclic images of something of these expressions, which are quadratic in Plukers. So, and the whole, if you want a function, I won't be talking about this functions here. I'll just wrote it just so you know, the polylog functions are a bit more complicated, and the expression looks something like this. Okay, and now why don't we start increasing the 8 points? So for the 8 points, the important progress came from the work So He, Li, and Zhang. in first paper 2019. So that's so here I copied the symbol alphabet for the 8 points. So you have 180 rational letters. So they're the plukers. And then you see what happens is there are these, quadratic and cubic function of these regular plukers. So that's a list basically, okay? So there are, okay, so various intersections. I'm not going to go in detail. There's spelled out in any paper you open. So there are these what you need to remember is there are 180 rational letters. They've done the computation for 8-point NMHV 2-loop amplitude. Okay, then there are 2 times 9 algebraic letters. They contain square roots of this following form. And there's another square root of where you basically shift by 1, 2, 4, 6, 8. You shift this indices by 1. So okay, very nice. So we would like to. That's what's known. And then actually on Monday I learned, and please correct me if you guys are in the audience. I think you're finding that for 3-loop 8-point MHV, I think you're finding. This is what I saw from your slide. Again, I haven't talked to any of you, but hopefully I got it right from your slide at poster session. I think you're finding these additional 24 letters, and they are of this type. Okay, I'm not going to comment on that because I only learned about this on Monday. Very good. So so we will just focus on this. And then for n equals 9, so again, work by Songhee, Li, and Zhang. Really remarkable computations. There are 59 times 9 rational letters, again, copied straight from their paper, and 11 times 9 algebraic letters with square roots, which are roughly of the following form. Okay, so that's a simple alphabet, the results of the actual computations for this n equals 4 Yang-Mills theory. So what's the point? Why am I here? So we'd like to take this as a given. We'd like to take this results as a given, and we'd like to find a mathematical description of these symbol letters. So that's the kind of our main goal. And that's, so if you missed what I said, so that's the problem we'd like to solve. Okay. Now, before we go to 8 and 9, I have to remind you what's the story for 6 and 7. So a long time ago, we observed that these letters, that these 6 and 7 point letters are nicely described by cluster algebra. Okay, so I'll just have one slide on that. So so there's a number of points n, and the cluster algebra is Grassmannian cluster algebra 4, n. Okay, so to define, I just have one slide. Some of you know it, some of you are new to this. So, and then it would be just an overview for you. So a cluster algebra is defined by 2 things. Is defined by initial quiver, and I wrote to you the initial quiver for GR4n, which looks like this, and a certain mutation rule. A certain mutation rule, which is given from the quiver. You can write down for a generic mutation rule like this. And what you do, you mutate each node and you produce a list. And this list is called all possible cluster coordinates. Okay, so if you're not familiar with this, so cluster algebras were invented in 2002 by Fomin and Zilevinsky, and the Grassmannian cluster algebras come from papers by Scott, Geffman, Shapiro, and Weinstein. And it's a very nice cluster algebra portal, which is being kept by Fomin right here. So any conference, anything on this field is listed there. It's quite amazing. It's a very important and interesting area in mathematics. It has applications in also to physics. There are lots of conferences. There are graduate level courses that are taught on this. But this is all we would need to know for our discussion here. So for 6 and 7, as I said, so this is generic G4n. So what you do, you rewrite them as you take this quiver for GR for 6 and GR for 7, and you mutate each node. So for example, I mutate 1, 2, 4, 5, and I produce a new quiver, and then I continue until I stop, and I generate the 15 cluster coordinates, which coincides with the n equals 4 Yang-Mills theory symbol alphabet. I continue doing that for 7 points. There are 833 quivers. You reproduce 49 cluster coordinates that exactly appear in the n equals 4 Yang-Mills theory alphabet. So very good. Okay, so that's been known for a long time. Now we want to, since there are new computations that's been done by Song et al., we would like to see what happens for higher points. So of course, it's been known since our original work that for GR for n greater than 7, cluster algebra number of cluster coordinates become infinite, and that's been known since Fomin and Zelinsky. And now, I mean, this also been known, but explicitly done by Song-Hee, Li, and Zhang, the simple letters start involving square roots. And in cluster coordinates, in cluster literature, you usually have, these are just, you usually have rational functions. So we would like to explain these two new features. Okay, so we'd like to build up an object which has, what is, so for 6 and 7, we had an independent, we had the Yang-Mills computation, and then we had a mathematical construction which produces this. We want to do the same. So what is the mathematical description for this case? Okay, so there's been several approaches to this. I've listed 5. So at last Amplitudes, we heard from James and we heard from Mark. So James et al. And collaborators have this approach using tropical geometry. I'll have one slide of that, but you heard James's beautiful talk at last Amplitudes. And there's also an approach using dual polytopes, and Mark gave a talk at last Amplitudes on that. I'll have one slide about that. What I will talk about, I will describe to you what we've done in the last year, some completely different way of looking at this, and there are 2 different independent ways. So one using Plabic graphs and the other one using tensor diagrams. I should also mention, I won't have a slide of that. There's also a very interesting paper by Henrietta's student, Aidan Herdershi, who used scattering diagrams. That's another area in mathematics, and who's finding also some interesting things. I won't have a slide actually on that, but that's the 5th approach. Okay, very good. So now I am going to maybe say 2 slide or per each of these. So for example, tropical geometry, as I said, James gave a beautiful talk last year. So, there's this seminal work by Spy and Williams, who associated a fan to the positive Grassmannian by solving tropicalized Plucker relations. And what Drummond, Forster, Gudagan, Kalusius did, they looked at a smaller version of this fan by looking at particular Plucker coordinates. So they didn't look at all. They have, they looked at some, and then they looked at the rays that you get from that picture, and those rays are G vectors for cluster coordinates, and those are the cluster coordinates that include all these 180 rational letters for n equals 8. So from all these, so you get all of these. So then there are exceptional rays, and from which they also were able to get the square roots. Okay, actually I should mention, then there was the work also for, so this is for n equals 8, and for n equals 9, this was also done by Yorgos Papathanasiou and Hinke. Okay, so there's this approach. Then there's a dual polytop. There's Akani Hamed Lam and Sparlin looked at polytops dual to these fans. They used this method of Fraser et al. And found evidence for the expected type of square root. So the goal was to look at the square roots. And so we will be using, in our tensor diagram approach, we'll be using part of that because they showed that these variables come from a generating function of the form. And if you look at the poles of this generating function, these are exactly the square roots that we're interested in. Again, so this you've heard This you've heard last year. So let me move on to our approach. So approach would be, again, as I promised, two approaches. One was from Plabic graphs, the other one would be for tensor diagrams. So, okay, again, so it's been, so Plabic graphs have been used for scattering amplitudes for a decade. There's a book by Jake, Nima, Yaroslav, and Postnikov and Goncharov. They've been used for integrand. Okay, so mostly we've been using for integrand as your book, and we've benefited tremendously from Jake's code, where you know, everything's been automated. So the building blocks of n=4 amplitudes are these Youngian invariants, which are given by these integrals, where you have the matrix C, K times N, matrix C, which parameterizes the cell of the positive Grassmannian. And it's known that such cells are in one-to-one correspondence with Plabic graph. So here I've drawn an example. So I'm sure you're over the, so the older people have heard this in the past 10 years quite a bit. The younger people, okay, I refer you to the book. So what are we going to do here? So what are we going to do? We're going to start with the Plabic graph, which will come with some matrix C, which we're going to, so we draw a picture, we go to Jake's code, we write the matrix C, and we're going to solve CZ=0. Very, very simple. And then we're going to compare to the known symbol letters. I should also say that simultaneously with us, there was a work by he and Lin, who also did the 8-point square root. Okay, so example. So for example, this is a 6-point Plabic graph. You parameterize it, you label it by phase variables, and then you solve CZ=0, and you get, so all the entries in C you have given in terms of the F's by this formula, and that's it. So this you can actually give to students and undergrads to generalize. It's nothing you need to know. So just algebra, you solve, you know, CZ=0, and that's what you get. And then you look at what letters what letters appear here. Okay, so the letters could be summarized in this case by the following quiver. So these are the letters that appear, and then you continue. You write down all the 6-point graphs that you can write. You solve CZ=0, and you see what the letters. So not very, very nicely, we exactly reproduce the 6-point alphabet by this. So the procedure is very, very simple. You move on to 7, you reproduce 7 points. Okay, so very good. So now we move to 8. Okay, so before you start doing 8, you need to reproduce, you know, 6 and 7. Very good. So good. So here's a graph, and it gives you, boom, it gives you 8 algebraic letters, but they're actually 9. Remember, they're 2 times 18. So what you need to do some, if you make actually a square move on F3, then you get the 9th square root, and then cycling by 1, we can reproduce all 8, n=8 algebraic letters. Okay, very good. So sounds good. Except that you also want to get all the rational letters, and you probably want to have something systematically. So it turns out that so we have a list, right? So we just take this list, and where is it? Yeah, the list. Okay, so this is the list we want to reproduce. These are graphs, right? But it turns out that if you just restrict to Plabic graphs, oops, where is it? You can't get all the rational letters. So good. So what to do? So we had to consider some non-Plabic S matrices, C matrices. Okay, so for example, what's that? I'll just sketch the situation. So for example, you look at this graph. What you need to do, you need to mutate on a face F8, and this gives you some non-Plabic C prime. So then you solve this with the C prime. So you solve the CZ=0 with that C prime, and then you get, so then you are able to get all the rational letters. So, and once we start doing this, we means the students and postdoc. In some cases, solutions start involving non-cluster coordinates. So that's another thing that was puzzling. But we showed that then okay, we start thinking, okay, so how do you know what class, what graphs to start with? Well, one thing we showed is that restricting to the top cell, setting k equals n minus 4, but allowing arbitrary non-Plabic C matrices would always produce cluster variables. So that's one statement we proved. But to summarize, what we've done, we've identified a set of graphs that reproduce all known 8 and 9 point symbol alphabets. Okay, so we have the graphs, but we don't have, unfortunately, we don't yet have a theory to explain the pattern of which cells associated to which symbol letters observed in Amplitudes. So it's kind of phenomenology that we're doing. We have the list, we look, this graph gives this graph is this list. I wish there would be more systematics, and I think there's a lot more to be done here, a lot more to be understood. And I think that also it would be nice to have more data from Jan Mil's side. So eventually, I think, you know, I don't know how long it's going to take. Eventually, when there are more amplitudes, as more amplitudes are being computed, I think there would be a process, or for example, you know, for some of them, we have the path that gives us this, and then these are like, you know, length 5 paths, and you know, Anders and Akshay and Jorge, they basically just really doing, you know, they start with some graph, they see what you get. That's the way we're doing it. But it certainly would be nice, and it's an open question to have this more systematically. Okay, but so this procedure is very simple, and we can get those lists, but more systematics and more understanding, and hopefully more understanding from mathematics. You know, what graphs to start with, which length, how long, you know, what you do. So still more to learn. Now let me tell you about some other another approach. So now I switch gears to bringing on a different type of mathematics. So this is our work with Li Cheng Reng and Mark. So there's in cluster, so again, as I said, cluster algebra literature is a huge subject. And there's something that's known as tensor diagrams. So these were first applied to, these were first discussed by Fomin and Pilavsky in an application to cluster algebra. It's actually the paper on archive of 2012. So they, the claim is that those cluster coordinates, cluster variables, can be represented by tensor diagrams. So who are these tensor diagrams? So I will be very brief. So this none of you heard. This is a new mathematics being used for amplitude. So so let me just quickly. So endpoint SLK tensor diagram. You take you draw a graph inside a circle with n marked points, and these are some rules. All boundary vertices are black. Each internal vertex may be black or white, but must have valence k. So we'll be talking about SL4 and well, SL3 is an example, and each edge must connect a black and white vertex. So these are known. So that's what these diagrams are. Now I need to go to, and now to each diagram, one can associate an invariant. Okay, so that you encode these cluster variables by these diagrams. So first, to each external vertex, you associate the momentum twister. So for this one would be, you know, Z1, Z2, Z3, Z4. Then you have a epsilon tensor to each white vertex, and the other one for each black vertex. And then you contract indices as indicated by the edges. So for example, for this diagram, the corresponding invariance would be something like this, 1, 2, 3, 4. For this diagram, the corresponding invariance would be something like this. And for this one, etc., there would be something like this. Okay, so very good. So these are the tensor diagrams. Now, and to each diagram, you associate a tensor invariant. So these tensor invariants are invariant under graphical moves, which are called skein relations. And I've drawn some of them here. This is just really give you a flavor, but you can open Fomin and Pilavsky, and yeah, if you'd like to learn more. Now comes the Fomin-Pilavsky conjecture, and that's the following. So first, let's call a web a planar tensor diagram. And second, we're going to call a web arborizable from obviously arbor, French word for tree. So right, yes. So arborizable web is the web that can be turned into a tree diagram using this skein relation. So here, for example, I have an example. You have this, okay, is it visible? Yeah, you have this diagram. Okay, it's not a tree, it's got a loop. But now take these blue lines and apply these two skein relations for them. Okay, so you can see that, okay, can I see this? Yeah, so if you apply this, you can turn it into this, okay? Through this, and one of them gives 0. So in the other one, yeah, so on the left-hand side, you have this, and then you make it into this, which gives this, and then this one gives 0. Okay, so this, so arborizable web, you can turn into a tree diagram. Now the conjecture is that is the following: that these tensor invariants for an arborizable web are in one-to-one correspondence with cluster variables.
5 minutes, Anastasia.
Yeah, that's, I'm almost, So I have 2 more slides. Are in one-to-one correspondence with cluster variables. This was also proven for some of these by Chris Fraser. Okay, now, good. So we could get, of course, all the cluster variables from this tensor diagram due to Fomin-Pilavsky conjecture. Okay, what about the square roots? Okay, so this is the up. So we had this long paper. So this is the up shot of the paper. So this is what we propose. We propose to look at almost arborizable webs. So something like this, which basically can be reduced to have only one inner loop. Then what we do, we assign some, so this is very much in spirit of Arkani, Hamed, Lama, and Spralin. We assign to them a web series. We have some graphical rules how to get the coefficients. Again, the details are in our paper. And then we sum this series, and we show that this series takes this form. Okay, where A's and B's are these guys. And then we see, okay, the square roots. So if you look at the pole of this generating function of this series, the poles of this are at these locations, and boom, this is exactly the square root that we see at the symbol alphabet. So that's the procedure. So we look at almost arborizable webs. So rational letters are all in arborizable, but here we look. Oh, I should have made this almost in blue. Okay, we look at almost arborizable webs, and from them we can get the square roots. And we've done this, and most credits should really go to Li Chengren, who hopefully is here. So he's done a lot of very, very difficult work. So he reproduced all the square through this procedure. The square roots for 8 points and 9 points have been reproduced. It's a very hard work. Okay, so that's the second approach of our tensor diagrams. So now I conclude. Okay, so a summary. So it's been known for a decade that symbol alphabet for n equals 4 Yang-Mills amplitudes is described by cluster algebras for 8, 6, and 7 points. And starting with 8 points, one needs a mechanism producing finite subsets of these cluster algebras and also to produce the square roots. I presented to you the 2 candidate mechanisms, coming from Plabic graphs and the second one coming from tensor diagrams, where we could reproduce these results. Although again, I should say, I learned on Monday about these 3 new letters. One certainly is on our list. 2 others we discussed yesterday with students. Yeah, I think we should look at this. The conference takes so long, but we've been looking at these two. But I hope they are also there. So, but in the future, it would be nice. There are lots of obvious questions, lots of work. It would be nice to have this more systematically, especially with Plabic graphs. It would be good to do more examples on the amplitude side. I hope Lee and Zhang can help. And of course, this all. Everything I talked to you, I just talked to you about the problem of mathematical description of the symbol alphabet. Of course, then you would like to study functions and cluster adjacency and, generalize some of these methods to non-supersymmetric angles. So I will stop.
Thank you, Anastasia. Let's all unmute ourselves for a minute and give Anastasia a round of applause. And let's remute ourselves. We have one question from.
Okay, so there's a
Yorgos.
chat. Hold on, let's. Yorgos is good, but I want to hear from Chi. Chi Zhang has a chat.
Yeah, why don't we take Yorgos's question first, and then
Okay.
I will go to.
Sure.
And thanks for the nice review and talk, Nastya. Could you go one slide back?
Yes.
Okay. So just to clarify, if I have understood your paper correctly, and also Ren, yes, Li Cheng's presentation at the MITP workshop.
Here, right?
Yes.
Is self-visible because he's really done this work.
Yes. So it's you obtain the correct square roots that appear in the algebraic letters, not the algebraic letters themselves.
Correct. That's
Is
correct.
that correct?
That is
Okay.
exactly like this is if you look at Lam and Nima and Mark, that's exactly the same spirit.
Mm.
Yes. Mm-hmm.
Okay. All right. Because the title might be a bit confusing. If you
That's exactly. That's why I keep. Yeah, exactly.
All right. And since you also gave a beautiful yes status of the field yes earlier on, and thanks for mentioning also the review my collaborators and I have written, and also my work with my student Niklas, the recent one about the 9 particle case. Let me just add that in our case we do obtain the correct square root letters for the 9 particle yes NMHP amplitude.
Yeah, let me just say, in tropical geometry, you get them. The same in Plabic graphs. In Plabic graphs, you had the thing, right? Yes, absolutely.
Plabic graphs is a postdiction rather than a prediction, in the sense that you.
Plabic graphs, okay, so between me and you, Plabic graphs is my favorite. Okay, why? Because it's so simple. You have the Plabic graph, you get all the square roots. So this is a, you get these. So to me, this is the nicest. Okay.
But correct me if I'm wrong. With Plabic graphs, one cannot make a prediction. You make a postdiction. Namely, you pick a particular alphabet, and then you look for which Plabic graphs.
No. You look at the graphs and you see what the candidates are. Okay.
Well, you mentioned earlier that you started with a known alphabet and then looked for which Plabic graphs reproduce it, right?
But you can also start with Plabic graphs and see which square roots you obtain. Yes.
One can certainly try this.
There's square roots, there's algebraic letters, and there are rational letters, right?
Mm-hmm.
Okay. So for square roots, I think it's pretty clear. You take Plabic graphs and you get the list.
You
okay?
Get the list
for rationals, you have to be a little, it's if you want just this, so I can tell you what I think. I mean, I think eventually the full alphabet is going to be bigger. Okay. So just already you see they got 3 already they're getting this 3 loop ones, they're new letters. Okay. So eventually, I think on both sides, work needs to be done.
Okay. Yes. If I recall correctly, yes, you can look at Plabic graphs and investigate which of those reproduce a known alphabet. But then are you saying that if one looks at, I don't know, all Plabic graphs of intersection number 2,
So
one gets all square root letters, or?
Yeah, eventually, this is, we don't have that yet, but eventually there would be a rule, which there will be a rule which Plabic graph to take to get these letters, okay?
Okay, I hope so, because right now, if I understand correctly, one needs to either restrict to, as you said, Plabic graphs, and this gives you only the square roots, but not the rational letters, or you lift the Plabic graph constraint, you consider more general graphs, but then you're completely in the dark in order to get the rational letters. There is no guiding principle.
You see which mutations to do, and Anders and others, they look at length 5, for example. I'm sure you heard this, and yeah, but Plabic graphs is very simple. You don't need you don't need tropical geometry, blah blah blah. This is a very simple approach. Yeah. So that's my favorite one. Everybody is free to have their own favorite ones.
Okay, yes. I don't think tropical Grassmannians are that complicated either. They're just linear objects. Really.
It sounds as though we should have a rematch of this discussion.
Favorite.
We should have a rematch of this discussion next year, perhaps the year after. Before we go to Matthias and to Yaroslav, in fact, if Zhang wants to make a comment, please go ahead.
I just want to point that the two-loop amplitudes are computed by Simon, not two-loop 8-point and 9-point are computed by Simon, not us.
Yes. That's what sorry, I should have maybe had Simon earlier. Of course,
Yeah,
I mean, anyway,
it's just. Yeah.
Thank you, Chi. But Simone and I were in Santa Barbara when Simone posted this paper. So of course, I'm in 2010. You probably were in kindergarten, but of course, thank you, Chi. But of course, two-loop MHV were done by Simone, and you've done NMHV. Yes, maybe this. What are you saying? That maybe list should be better? Yeah, is that what you're saying?
I mean, the last 2 points you said n equals 8 and 9 MHV 2 loops. Actually, these are not computed by us, by Simon.
Yeah. Simone computed MHV all 2 loops, of course.
Yes.
Yeah. I think I was at the same Santa Barbara workshop when he posted his paper. Okay, thank you.
So yes. We have a question from.
I should add this. Are you saying I should add Simone here and Simone?
No. I mean, yeah, I think it's the fifth point. The fifth point.
1, 2, 3, 4, 5. Yeah.
Yeah, you said it's n equals 8 and 9 MHV.
And for MHV Simone. Yes, I thank you. Last night I was editing because I saw your poster, so I re-edited this slide actually very quickly because I had to add your. I'm very impressed with your. Actually, I'm very impressed with your these 3 letters that you find. Yeah. Okay.
So we have a question from Matthias.
Hi, thanks for the very interesting talk. So as Jill will tell us more about on Friday, we actually have elliptic symbol letters at 10 points in cubed MHV. And I was wondering whether your techniques that you presented in the talk can actually reproduce these.
Okay, to me, this is very interesting. I think Mark was more of an expert on this, so he's been thinking about this. Very interesting. So, but I think I should add you citations explicitly. I think I said this, but I didn't write. Of course, I am just limiting to this. Would be very interesting. Yeah, I think that would.
Yeah, I mean, I don't mind appearing on or not appearing on the slides. I'm just honestly interested in which of these many proposals can actually generalize to the elliptic case.
Yeah, I think this would be very interesting to look at.
And I guess we have now a question, if I'm understanding correctly, from the surface of Mars by Yara.
Yeah, I just have a question about these non-Plabic graph symmetrices. So is there anything interesting about these symmetrices, or are they special still in some sense?
Yeah, I tell you, we just mutate. We have these mutations length 5, and I think it would be interesting to understand what is exactly are the mutation sequences which give them. But on one hand, it's an interesting problem. On the other hand, I do think that, you know, the alphabet that there is on the Young-Mills side, which we're trying to reproduce, might not be the, you know, might not be complete. So maybe, yeah, I mean, as I said, what we're doing is just mutating, length 5 gives the, and stop as soon as we get the known alphabet for 9 points at least.
Mm-hmm.
I think would be very interesting to you know, for many years I've been going around saying, okay, there are these red and green mutations, these are known in mathematicians, but nothing, I mean, there's nothing concrete we can say. I think it would be nice to say something concrete. Yeah. Mm-hmm. I think Nima.
Okay, thank you.
There's a question from Nima.
Yeah, Nasia, just a quick comment and a question, or maybe the question first. So there are these sort of non-cluster objects that show up as the face variables. I'm wondering if it's possible to sort of decide which ones are good and which ones to throw out just from positivity. Is it true? I'm guessing it's true, but I'm wondering if you've checked explicitly that these sort of non-cluster things that show up have the property that they can go negative when the external data is positive.
Okay, let me call on, I don't think we checked this. So we have this way of getting rid of non-cluster variables by restricting to the top cell. That we have. Now
that gets
non-cluster, yeah. But we have to
that gets all the cluster variables, or it just produces cluster variables?
It produces cluster variables, yeah.
But all the cluster variables? I mean, all the ones you want, or just
all the ones we want? Yeah, all the ones. Yeah.
Okay.
But we have to allow for non-Flabby.
Okay, good. And then, okay, great, thank you. And then I have the comment is that this way of talking about sort of C dot Z equals 0 and so on. I mean, it's very clean and it's a nice formal statement about the Plabic graphs. But I think there's something very physical about it. These are, after all, leading singularity diagrams. They're not like random things. They're literally leading singularity diagrams. And these functions that you get associated with the facets are associated with the geometry of the leading singularity solutions. So there's something very interesting and physical about the fact, for example, in the famous 4-mass box case, and now going to sort of Giorgio's point, not just the argument of the square root, but the entire damn letter is the cross ratio of the line that intersects all 4 lines that you get in the leading singularity problem. Okay, so in the 4-mass box leading singularity problem, we have the 4 lines at 8 points. We have 4 generic lines in P3, and there are 2 Schubert lines that intersect all 4. For any one of those lines, there are 4 marked points on the line coming from the intersection point. And the cross ratio of those 4 points is literally the whole object that shows up in the symbol. And in fact, you can interpret all the things that show up in the symbol as cross ratios of 4 points on the line. Various interesting 4 points on lines in that example. So there's something quite deep about this, is that we see that the symbol letters that you're identifying in this way, and just a sort of Plabic graph way of finding them, is just a connection between Plabic graphs and leading singularities. But the fact that these are the objects that you're getting are telling you the symbol is occurring when the actual leading singularity solutions exhibit some kind of degeneracy. So I think that's a kind of physical reason for looking at this. Of course, the reason you gave is perfectly good motivation, but I just wanted to mention that it's not. There is also that there is a sort of direct relationship to the picture of leading singularities.
Yes, Nima, I completely agree. Yes, I completely agree, except that when one has the list and one has to reproduce, then one gets a little lost. But yeah, I completely agree. Yeah.
Well, just to make one comment about this, if you think about the geometry of leading singularities, it actually doesn't know about K. So it unifies all the different Ks into sort of one object. And these problems are likely essentially identical. Anyway, but yeah.
Lance?
So we heard in the, I guess in the poster session, although I missed it too, this new experimental data from 3 loops,
Yes.
n equals 8. So I I assume, and Qi Zheng can correct me if I'm wrong, that this came through the analysis of the Q-bar equation.
Exactly the
So,
same.
so I think maybe the geometry of the Q-bar equation is something that, you know, needs to be thought about more generally, maybe. Maybe that's easier said than done, though.
Yeah, it's easy for me, you know, when I hope they will have more results. Yeah, again, I went to just browse what was at poster session, and I see the last slide and I'm like, whoa, how did it happen? I mean, I didn't, yeah. So maybe, do you guys want to say something, Lee and John?
Yeah, it's just we just compute this by using Q-bar equation, and this is 8 orbits compare with, I mean, 3 new orbits compare with the 2-loop n-geometry, and but I think these letters fall in the prediction from the tropical Grassmannian.
Were they there in tropical Grassmannian literature by Yorgos? Were those letters on your list?
Sorry, what is the question?
Were these 2 letters on your list?
This is something that it has not been checked yet, but we certainly have a much larger list of letters. So as you said,
so are they on your list or not? Are they on your list?
First of all, a correction. Yes, you mentioned that James did the 8-point analysis. With my student, we also did the 8-point analysis, at least the rational part. And there are 272 rational letters for the 8-particle case.
Yeah,
so
list. That's what I'm asking.
Well, the authors of this paper that came after ours should probably say this is in the list. I believe it should. Yeah, I believe it should be there.
On the list, yes.
I think
I think you say no in your poster. Yeah.
I don't.
Yeah. Okay.
Yeah, I mean, I think we compare with from the prediction. I will compare with the prediction from the James, but yeah, I could remember that. Sorry.
You can check. Yeah. Okay.
Yes, the rational letters, of course, all 3 papers predicted. James's paper, our paper, Nima's and Mark's paper, and so on.
Yorgos, we
agree on the 272 rational letters.
Yorgos, do you hear me? We're talking about the new result from Monday. These 3 letters. You see the one in white? They were not.
Yes.
They were not there. They're only in the poster session slide. They're not in the literature.
They're not in the 272, right, Anastasia?
I am saying that yes, there are predictions for 272. You have it also on your slide. 8-point letters from both the tropical geometry and the dual graph picture.
I think you don't understand what I'm saying. Okay, I'm saying that on Monday there's a poster session where they have these 3 letters and they say they're not on the list. Okay.
This is in the. I didn't see this in the poster, but it said that it's not.
You didn't. That's what I'm telling you. There are these 3 letters that are not in your paper, not in our paper. You know that's all. Okay. I'm talking about this result from Monday, not all the literature.
Okay, and so Chi, you said you confirmed that you compared with James and you did not find them. This is what you said.
No, I think, yeah, but I believe, I mean, sorry, I don't remember that, but I think
that's what I understood. You said you didn't remember.
No, sorry, I will compare with some prediction, but it's come from Lee. I don't know where he's him, but I just remember that our new letters fall in some prediction, but I forgot which prediction by whom.
Okay.
But they agree or they disagree?
Hmm?
But they agree or that they disagree? They are not contained.
Sorry.
You said you compared with one prediction. Okay,
yes.
All predictions agree on the 272 letters, so that's fine.
Yes.
But you don't remember if this comparison with the predictions agreed or disagreed with your new letters?
Yes.
Okay, this is what I understood. Okay, this needs to be checked.
Sorry for that. Yeah.
No worries.
That's precisely why I said the comments, you know, I'm not going to comment on this. I'm just pointing out to everybody that there's this results in the poster session that I was very happy to learn. And looks like I'm not the only one who didn't know. It looks like, yeah. That's all.
Yeah, we still want to do with this result, so that's the reason why this paper not appear.
Yeah, but I think it's what you're doing is very important. So Chi, it's very important that you're doing these computations because one needs more data. Then one needs solid data from the amplitude, the Q-bar equation to then one can study mathematical structures, etc. So
yeah. We just, we obtained this data 2 weeks ago. So
yes.
If I'm not mistaken, you're speaking on Friday, right? So,
but he's not talking about this. He's talking about.
I understand that, but perhaps with the chairman's indulgence on Friday, he can spend 5 minutes clearing up this question.
Yeah.
So, are there any other questions? We've had a very spirited discussion. If not, then please let's unmute ourselves and give Anastasia a round of applause. And let's also thank the